In the last lecture, we have covered that how to find out the Fourier transform of some functions as well as what is the Fourier transform of the Dirac delta function and some useful values of some given integrals. Now, let us take some other type of problem. Let us see this one. Express the function f x equals 1 and 0. Whenever mod x less than 1, it is 1. Whenever mod x greater than 1, the value is 0. We are saying that you express the function as a Fourier integral. That means f x in terms of Fourier integral representation, we have to do it. Fourier integral representation means where the function is coming as an integrand inside the integration sign. So, my first job is to express the function f x, which is defined like this as a Fourier integral, and then whatever result I will obtain, using that result I will try to find out the value of 0 to infinity sine of lambda x cos of lambda x by lambda into d lambda. Actually, here one x will come in this place, sine of lambda x into cos of lambda x by lambda. So, let us see the value by Fourier integral formula. Please note this thing, by Fourier integral formula, your f x, if you recall, we can write down f x equals 1 by pi. Here I have two parameters, one is lambda, another one will be some other parameter, say t. T equals will be minus infinity to infinity f t into cos of alpha into t minus x dt d alpha. This again I am not explaining, because already we have done towards the introductory lectures of the Fourier transform. When we started, we explained all these things. Recalling those things directly, I am writing the Fourier integral representation of a function f x can be written as this one, f x equals 1 by pi alpha equals 0 to infinity, t equals minus infinity to infinity f t into cos of alpha into t minus x dt into d alpha. Let us evaluate this one. Please note this, that your f t is nothing but 1 whenever your modulus t is less than 1, because your f x was 1 whenever modulus of x is less than 1 and it is 0 whenever modulus x is greater than 1. So, I will only consider this part, that f t equals 1 whenever modulus of t is less than 1. So, by remembering this thing, these particular integrals I can now write down alpha equals 0 to infinity, it will remain as it is. Now, t will vary not from minus infinity to infinity, but it will vary now from minus 1 to 1, because in all other ranges, in all other intervals, the value of the function f t equals 0 for modulus of t is greater than 1. So, using this one, I am changing the limit as t equals minus 1 to 1, your f t now is 1. So, you are writing 1 into cos of alpha into t minus x dt into d alpha, and this integral I can evaluate it very easily. So, that I will obtain the result as 1 by pi alpha equals 0 to infinity. Here it will simply coming as sine of alpha into t minus x by this alpha will come, where t will vary from minus 1 to 1 into d alpha will be coming here. So, once I am getting this, if I substitute the value over here, actually you will obtain this integral. Alpha is varying from 0 to infinity. This will be sine of alpha into t 1 minus x will come, minus sine of alpha into minus 1 minus x will come by alpha into d alpha. Just you are substituting t equals 1 and t equals minus 1 over here. So, therefore, what you are getting? You are effectively you are obtaining that f x equals, your f x is nothing but this integral sine of this plus this. So, that in the next line the last integral again I can write as 1 by pi your alpha equals 0 to infinity sine of alpha into 1 minus x plus sine of alpha into, it will be 1 plus x, that minus will be changed. The term was minus sine alpha into minus 1 minus x, which will be plus. So, that now it becomes plus sine alpha into 1 plus x divided by alpha into d alpha. So, that it is in the form of sin c sin d format. So, this equals 1 by pi into 2 0 to infinity sine of alpha into cos of alpha x by alpha into d alpha. And this I can write down in the form of alpha. I can replace this, simply I can write it as 2 by pi 0 to infinity sine of say lambda into cos of lambda x by lambda into d lambda. Therefore, if I give this one, then 1 basically now I can tell 1 represents f x as Fourier integral. So, please note this one. So, you are obtaining the Fourier integral of f x as this thing. So, from other way I can tell that from 1 0 to infinity sine of lambda into cos of lambda x by lambda into d lambda, this is equals pi by 2 into f x, and your f x you know it, f x is 1 for modulus of x less than equals 1, 0 otherwise. So, that this equals, you can write down pi by 2 whenever modulus of x is less than 1 and it is 0 for modulus of x greater than 1. So, I have done two things basically. One is, at first I represented f x as an Fourier integral by this way, which is represented by equation 1, and from equation 1 directly you can tell that the value of the given integral is pi by 2 whenever mod x less than 1 and 0 whenever mod x greater than 1. So, this shows how to represent one function as a Fourier integral. Let us recap this thing. Just you see that the express f x equals this thing as a Fourier integral, and hence evaluate the given integral. So, in the initially by Fourier integral formula is this one, f x equals 1 by pi alpha equals 0 to infinity t equals minus infinity to infinity f t into cos of alpha into t minus x dt into d alpha. Again, please recall that this we have discussed at the beginning whenever we started the Fourier transform. Then we have made the Fourier integral representation, and we have shown you that using this Fourier integral representation, how I can find out the Fourier transform, Fourier cosine transform or Fourier sine transform. So, we are writing this one expression very easily here. So, now your function f x is defined as f x equals 1 whenever mod x less than 1 and otherwise it is 0, that is for mod x greater than 1 the value is 0. So, once I am using this thing, therefore, the limit of t now will be restricted from minus 1 to 1 only, because in minus 1 to 1 your f t is 1 and in all other cases value is 0. So, I am writing 1 by pi alpha equals 0 to infinity t equals minus 1 to 1 cos of alpha into t minus x dt d alpha. So, once I have done this thing, then I can easily obtain the integral value of the first integral, inner integral, which is nothing but sin alpha into t minus x by alpha. So that you will obtain this one, f x will be 1 by pi 0 to infinity sin of alpha into 1 minus x plus sin of alpha into 1 plus x by alpha into d alpha. So, use the formula of sin c plus sin d, you will obtain this, and I write down it as 2 by pi 0 to infinity sin lambda by cos of lambda x by lambda into d lambda. And this one represents f x as a Fourier integral. Again, from this one I can write down the value of the integral is nothing but pi by 2 into f x. So, that only I am writing from 1 value of the integral is pi by 2 into f x, and you know what is f x. F x is 1 for mod x less than 1. Therefore, the value of the given integral will be pi by 2 whenever mod x is less than 1, and it is 0 whenever mod x is greater than 1. So, this particular example represents that how a function can be represented in terms of the Fourier integral, and using that one how to find out the value of some integration. Now, let us take the other example. Find the Fourier cosine transform of e power minus a into t square. So, for this one we have to find out Fourier cosine transform of e power minus a t square. Again, from the formula root over 2 by pi 0 to infinity e power minus a t square into Fourier cosine, so multiplied by cos of alpha t into dt. Say this is equals to I. This ever entire integral equals to I. Now, if I differentiate this with respect to alpha on both sides of this given equation, that is, you will obtain d I d alpha. This is equals minus root over 2 by pi 0 to infinity. If you use differentiation under the sign of integration, you will obtain t e power minus a t square, because cos of alpha t is there, and here you will obtain sin of alpha t into dt. So, basically what you are doing? You are just differentiating with respect to the variable t on both sides, not with respect to t, but with respect to alpha on both sides of the given equation, and using differentiation under the sign of integration, I am just writing d I d alpha equals minus root over 2 by pi 0 to infinity t e power minus a t square into sin of alpha t dt. And this equals, if you simplify it, I can I write down this thing 1 by twice a I will write down into root over 2 by pi 0 to infinity sin of alpha t into d of e power minus a t square. Can I write down this? That is the reason 1 by 2 a is coming, because this is 1 by 2 a t. So, this I am representing as d of this thing, so that it becomes easier for us to integrate the function. For that reason, I am rewriting this as d of e power minus a t square. Please note this thing. So, that this and these values are same. To make it same, I had to make divided by 1 by 2 a, because minus 2 a is coming over here. This minus is being cancelled over there. So, d I d alpha becomes 1 by twice a root over 2 by pi 0 to infinity sin alpha t into d of e power minus a t square. So, that I can write it as 1 by 2 a root over 2 by pi will be coming here, and directly I can write it as d of this. So, I am using integration by parts now, e power minus a t square into sin alpha t, where the limit will be from 0 to infinity. Second part will be minus integration of this part, that is minus alpha into 0 to infinity e power minus a t square will come into e power minus a t square into cos of alpha t into dt. So, using integration by parts, since I have written d of this, so it becomes easy for me to use the integration by parts. Using integration by parts, the first part I am getting as this, where limiting value is 0 to infinity, and second part is this integral. And if you see, if you evaluate the value of this, for 0 it is 0, this part will vanish, this part will vanish. For at t equals 0 and at t equals infinity, in both cases this will vanish. And what is this part? If you remember, I have chosen I as this thing, I was root over 2 by pi 0 to infinity e power minus a t square into cos of alpha t. In the last one we have told that from there only I obtained this we have written here, I is root over 2 by pi 0 to infinity e power minus a t square into cos of alpha t dt. This is your I. So, that this part is basically nothing but the I, this part vanishes. So, I will obtain, this is minus is there, alpha by 2a into I. So, you see, I have to evaluate the integral. What I am doing? I am just making the differentiation of the integral, and by making the differentiation of the integral, I will obtain one first order ordinary differential equation, which is d I d alpha plus alpha by 2a equals alpha by 2a into I equals 0, and whose solution I can directly write down I is equals to c into e power minus alpha square by 4a. Effectively, I am integrating on the both side of the given equation, and by integrating on the both side of the given equation, I will obtain I equals c into e power minus alpha square by 4a, where c is the constant of integration, whose value I have to find out. So, I started with the Fourier cosine transform of this integral, which is I assumed I. Then I am making the differentiation with respect to alpha on both sides, that is I am finding d I d alpha, and d I d alpha I am expressing in terms of I, so that I obtain one first order ODE, and by integrating on both sides I am obtaining the solution. My last job is to find out the value of the constant of integration c. So, your I is nothing but c e power minus alpha square by 4a. Whenever alpha is 0, what you will obtain? Your I at alpha equals 0. Your I at alpha equals 0 is nothing but root over 2 by pi 0 to infinity e power minus a t square into dt. You will obtain this, that I at alpha equals 0 equals that cos term will not be there. So, that will be 1. So, that 0 to infinity e power minus a t square dt. Now, put root over a into t, this is equals z. Substitute on this root over a into t equals z. So, that you will obtain root over 2 by pi 1 by root a will come here whenever you are integrating, differentiating, the limiting value will remain same 0 to infinity e power minus z square into dz. So, this was my actual aim, that since I know that the value of the given integral 0 to infinity e power minus z square dz is pi by 2, which we know very well. So, I am just using that one. I am converting the given integral in this form, so that I can put this value. So, I will obtain this one as root over 2 by pi into 1 by root a into pi root pi by 2. So, sorry, this is root pi by 2, not this one pi by 2, it will be root pi by 2. So, I am getting the value as 1 by root over twice a, 1 by root over twice a, root pi will be cancelled. So, at alpha equals 0, I alpha is this. So, from this given equation 2, if it is 2, from 2 I can tell that 2 implies now 1 by root over twice a, this is equals to c. Because your at alpha equals 0, your I is 1 by root over 2a, and when alpha is 0, e power term is vanishing. So that you are obtaining I equals, it is nothing but what you can say Fourier cosine transform of e power minus a t square. This is equals to nothing by, we assumed I, and this is equals 1 by root over twice a e power minus alpha square by 4 a. This is the required result over here. So, I hope it is clear that without evaluating the integral, by differentiating, I am converting the given integral in forms of some ODE or ODE of first order, second order it may come, and whose solution is very easily known to us, and we ultimately obtain the value of this. So, if I go through, then Fourier transform of Fourier cosine transform of e power minus a t. So, by formula of definition of Fourier cosine transform, I am writing this integral, and now I am differentiating with respect to alpha to obtain di d alpha, and di d alpha is nothing but this d of I am writing. So, that integration by parts I can use. I am using integration by parts. The first part will be 0 and second part is nothing but I. So, that you will obtain di d alpha equals minus alpha by twice a into I. So, that integrating on both sides of the given equation, I obtain I equals some integration arbitrary constant c into e power this thing, and I have to find out the value of c now. Whenever alpha is 0, your I at alpha equals 0 is this thing, whose value, if I put root over a into t equals z, then I will obtain the integral 0 to infinity e power minus z square dz, and whose value is root pi by 2. So, I am just substituting the root pi by 2 value. So, ultimately I alpha I at alpha equals 0 is 1 by root 2 a. So, that if I substitute, I will obtain value of c as 1 by root 2 a. So, I will become 1 by root 2 a e power minus alpha square by 4 a. So, this is another technique which we have told earlier also, to find out the Fourier transform of some function where we have to evaluate the integral. Let us take one more example, that find the inverse Fourier transform of e power minus t alpha square, where t is a parameter. Or I can pose the problem like this, that the Fourier transform of a function is known to me, which is e power minus t alpha square. I have to find out what is f x. Using the inversion, I have to find out this thing. So, let us see this one. So, Fourier inverse of e power minus t alpha square, this is equals 1 by root over 2 by pi minus infinity to infinity e power minus t alpha square into e power. This is only change will be e power minus I alpha x into d alpha, because whenever you are taking Fourier transform, this kernel is e power I alpha x, and when you take the inverse Fourier transform, then this kernel will be e power minus I alpha into x. So, now say alpha equals minus v by root over t 2t minus v by root over 2t, which gives your d alpha nothing but dv by root over twice t. So, that your t not t into alpha square, t into alpha square is your v square by 2. So, I am substituting here alpha equals minus v by root over 2t. So, that you will obtain d alpha equals minus dv by root over twice into t. This is root over twice t, and from here I can write down alpha square into t equals v square by t. So, that if I substitute this in the given integral, you can write down Fourier inverse of e power minus t alpha square equals 1 by root 2 pi minus infinity to infinity e power minus v square by 2 into e power I into this will become x by root 2 t into v into dv by root over twice t. So, simple calculations I am getting this. This equals, if you simplify, then you will obtain 1 by root 2. So, 2 will be coming here, root pi t will come here, minus infinity to infinity, e power minus v square by 2 into e power I into x by root t into v into dv. So, now you have this thing x by, if I assume x by root 2 t equals alpha, say suppose x by root 2 t is equals to alpha. So, I obtained this particular integral. So, that once I am writing this here, say x by root 2 t equals alpha. So, the integral of the RHS, if you see here, what is this one? Represents the Fourier transform of e power minus v square by 2, where the kernel is x by root t. Please carefully see it. This left hand side, right hand side integral, this represents the Fourier transform of e power minus v square by 2, because you are multiplied by this, and here kernel is not alpha, but kernel is this x by root 2 t, which is alpha I am assuming. So, e power, if I take x by root 2 t as alpha, it will become I v t, and then this will represent an Fourier transform of e power minus v square by 2 into e power I into x by root 2 t into v. So, please note, again I am repeating, this integral represents the Fourier transform of the function e power minus v square by 2 with the kernel x by root 2 t, not alpha. Now, what is the Fourier transform of this e power minus x square by 2? E power minus x square by 2 is self reciprocal with respect to Fourier transform. This problem we have done earlier. So, that Fourier transform of e power minus x square by 2 is nothing but e power minus b square by 2. So, if this is Fourier transform, then directly I can convert this with e power minus b square or minus, for simplicity make it minus alpha square by 2, and if I replace alpha by x by root 2 t, this will be the value of the given integral. So, I think this particular portion is clear, that this last integral represents the Fourier transform of the function e power minus b square by 2 with kernel as x by root 2 t, and I know Fourier transform of e power minus x square by 2 is e power minus alpha square by 2, since it is self reciprocal. So, using this particular form, now I can write down Fourier inverse of e power minus t alpha square. This is equals to, I am rewriting it, 1 by root 2 t into 1 by root over 2 pi minus infinity to infinity e power minus b square by 2 into e power I into x by root 2 t into v dv. So, that the inner portion is nothing but the Fourier transform of e power minus b square by 2, and I know the Fourier transform of e power minus b square by 2. So, directly if I substitute this, I will obtain 1 by root 2 t e power minus half into x by root 2 t whole square, simply by using the formula. Kernel is here x by root 2 t. So, this whole square e power minus b square. So, if I simplify this again, I will obtain 1 by root 2 t into e power minus half into x square by 2 t. So, that 1 by root 2 t e power minus x square by 4 t. Therefore, Fourier inverse of e power minus t alpha square is nothing but 1 by root 2 t e power minus x square by 4 t. So, quickly let us see. We are finding out this. We have to find out f x. We know the Fourier transform. So, using inversion formula I am writing this, and from there I am assuming alpha equals minus v by root 2 t. So, t alpha square equals v d alpha I can find out like this, and from here I am writing it as e power I into this part. Once I am writing this again I am writing just in the normal form, and as I have explained, the integral on the right hand side represents the Fourier transform of e power minus x square by 2 with Fourier kernel as x by root 2 t. Also, I know Fourier transform of e power minus x square by 2 is the function itself, that is e power minus alpha square by 2. Using this property I am rewriting and now finding the Fourier transform. So, it will become 1 by root 2 t into e power minus half into x by root 2 t whole square. And if I simplify, ultimately I will obtain the result as 1 by root 2 t into e power minus x square by 4t. So, you see, using the Fourier transform of something directly I am writing the value of an integral and I am evaluating it. So, I hope we have done various problems where various type of tricks, various techniques we have discussed, by which way you can evaluate the value of the integral for evaluation of the Fourier transform.